We're going to be introducing up here Alastair, who is going to be discussing the Novasaur TTL computer. It's been great towards just building this beautiful TTL logic computer inspired by some other designs that have been out in the community. Without further ado, let him begin.
Hi. So hopefully you can hear me. So I'm going to sort of like work off this screen, so hopefully it'll work out. But yeah, this is the Novasaur TTL computer. So this is a computer built from scratch. And you may be familiar with the Gigatron, so this is a very similar thing. And it's been about 40 years in the making. So this is me. That's actually, I think it was 1980. I was 12. So my first ever logic circuit was, I built a half add out of a couple of switches, and that was in 1979. So that was probably the first time I ever built anything out of digital electronics. So I was interested in electronics as a kid. And then I sort of had a ZX81 and Commodore 64 and all this kind of stuff. But I always liked the idea of building my own computer, and I was interested in sort of logic gates. And this design for the Novasaur really began in about 83, 84. And it was over the summer when I was at school. I sort of sketched out a couple of designs, and that was essentially the genesis of this project. I went on to college to do digital systems engineering, which I thought it would be like electronic engineering, but without the calculus, but it was a lot of calculus as well. I started in electronics, and then around about 91, I actually shifted more into production engineering. So instead of designing electronics, actually developing the production systems, test systems for the circuit boards. And then I went into more software testing, and then into actual software development. So that was pretty much the end of my electronics, around about sort of 91. Until this guy comes along. So the Gigatron was released in, I think it's 2018. And then there's the infamous Dave Murray video where he kind of talks about his dream computer, and that's the genesis of the X16. This is also the genesis of the Phoenix products as well. And it was also the thing that reminded me of this initial design that I had back in the 80s. I saw that video about a year after it came out. So it began in 2019. And so, yeah, it's been about 4 years. That was I would call that the Rev Zero board. So I did a lot of prototyping initially, just testing the pieces. And this was the first actual working version of this thing. That's about 6 months into the project. So we're 4 years now. The rest of the time's just been software development. And then this is the Rev A board. When I say A, I'm counting in hex. So this is the 10th revision. But that was pretty much about 2 years ago that was finished. So it's just been a lot of software. So the hardware requirements for this. So basically, I wanted to build something with like just basic building blocks. So the simplest building blocks, which basically like the simplest like TTL chips. But I wanted to stick with the 70s technology because when I was first working on this, that was kind of what was available. This was the early 80s. But I wanted to stick with that, so no kind of FPGAs or anything. I just want to keep to that sort of time frame. So it has to exist at the end of 1979. And it has to also be readily available today, 50 years later. So this is like, if you're in the 80s trying to find a 1930s vacuum tube. But there's a lot of 50-year-old technology still available. So that's the TTL chips. So 74 series TTL. I'm not using CMOS, so I actually want to use TTL, which uses a lot more power, and it kind of adds another layer of pain to the project. And scorched earth minimalism. So this was always like the thing I wanted to do when I was building this, is just like the minimum amount of stuff. But it kind of, not quite getting to like kind of like Turing tar pit, but just the most basic thing, but still be fast enough to be useful. So something that can be programmed and can actually do something that... The thing I worked on back in the 80s, that was like a really simple thing that would have a couple of buttons and some LEDs, or maybe it could print like prime numbers or something, but that's about it. But this one, I want it to actually do something useful and be a usable thing. So there's basically two computer architectures. There's the Harvard and von Neumann. So I don't know, you might be familiar with this, but basically, I think this guy is Howard Aiken, so he was responsible for building a very early mechanical computer. You can actually still see this in Harvard. It's named after Harvard, not him. The other guy was a bit more famous. So he wrote, that's the EDVAC. And so von Neumann read a paper, and then this was the kind of first implementation of that. And this is a stored program computer. So the program would come on a paper tape, and it'd be loaded into the memory. And then the computer's actually running the program from its memory. The Harvard Mark I, the punch tape is the program. So if you want to create a program loop, you take the punch tape, you connect it together, and then it actually reads the tape directly. And then you have subroutines, would be a separate tape. And so that's that machine there. So it has a data memory, and I think it's 23 decimal digits. So this is used for a lot of scientific computing and defense-oriented things. And the program memory, 24-bit instructions on a paper tape read by the machine as it's executing the code. But the important thing about this is there's two separate memories. These are completely separate. With the von Neumann architecture, you have a single memory that has program and data in it, but this one, they're completely separate. And that's what I'm doing here. So there's basically two memory chips. So these aren't 1970s technology. This is like the anachronism. These are sort of modern, but not ridiculous. These are still less than a megabyte. But you could potentially get the memory chips in the 70s. And you could basically build this, but it would be extremely expensive. You could probably buy a house for the same amount of money. So this is the Harvard architecture. There's an ALU, control unit I/O, and then there's the two separate memories. The program memory is typically going to be read-only, although it's potential it could actually update that. But typically this is a fixed, immutable thing. If you want to change it, you have to physically change it. And then the data memory you can read and write to. And you might think, well, this looks more complicated than it needs to be. But it allows you to do a very simple kind of addressing. And this is, I learned about the Harvard architecture at some point in '83, I think. I can't remember where, but when I learned about it, I'm like, that's really easy to make a computer. Because you don't actually need an address bus for this. But only if you have a single index. So I'm doing 16-bit addressing. But rather than having a 16-bit program counter, I'm actually using a page register, which is 8 bits, and then an 8-bit program counter. So the program counter, it takes a couple of chips. They're typically 4 bits, and then a buffer. But if you had 16 bits, that's 4 counters. So keeping it really simple, I have a single 8-bit program counter. And then what I do is, if I have to go beyond a page, I have to jump to a new page. And it resets the program counter back to the beginning, and then it will start to execute code in the next page. That does cause some fragmentation of the memory, of the actual program. But we've actually got a decent amount to work with in terms of memory. So single 8-bit page register, single 8-bit counter. And then there's the X and Y index registers for the memory. So there's just a single XY index, and that's kind of like the 6502 has that. So you don't have to swap it around. And that's where all those chips live on the board. So there's the two memories, those are the two program counter, 4 bits. And then there's a page register, and then the XY register. You might notice there's these resistor networks. They pull high, so you can actually default any of these addresses to FF just by not turning them on. That's used with the page register. So during boot, it just doesn't turn on the page register, and it goes to FF, and that's where the kind of boot code starts. And then you can also, there's a 0 page we'll get into later, but that's done the same way by pulling it to FF instead of pulling it down to 0. This is like a really cheap way of doing it. So we're going to sort of go through a minimal toy computer, which is actually not far off what this is. So we're going to load the instructions and then store them as a control word. I did have an instruction register, but it's not actually, the instructions are really telling the machine what to do, as opposed to, you might have an instruction which has to be decoded. This has all the information the machine needs to do something without very minimal decoding. And so that control word is going to define a source. In this simple example, we're going to use either the program memory or the data memory as our source. And then there's going to be an ALU operation to perform. And in this example, we're just going to add the accumulator, or we're going to add 0. And then the destination register is like where the result goes, basically. We can specify any of our registers, so we can actually send that to the program counter to do a program jump. And we can also specify the data memory. So we can read something to the data memory, we can update it, and then write it back. But every single instruction or control word is specifying exactly the same thing, just which particular flavor. So that means every instruction is an ALU operation. And every register essentially takes its input from the ALU. So the ALU goes to every register, and then you decide, based on your control word, which one you're going to load. And so that's our computer. So does it work? Well, the program memory, we're going to do a fetch, and it goes into our control word. And then we're going to have an input, either from the program or data memory. And then the result goes to the accumulator, or it goes to one of the other registers. And if it's in the accumulator, we can write it back to the memory. And technically, this kind of does work. And it's not, from a concept, this is sort of what's going on with the Novasaur. But you might notice some things about this. Like, let's say we wanted to write a program which is going to scan through the memory, and it's going to read bytes. We can only write to the X register. So let's say we want to read from the X register, update it, and write it back. Like have an X increment. So can we even do that? Well, this is where you have to use the memory to actually store your X value. Because we want to read that, and we only have this very simple structure. So we're just going to put it in a location, and I just chose this 3355. So that's the Y register is 33, and the X register would be 55. So to load the X register with our index to get the X register, we have to use an ALU operation. So we're going to load 55 from the program memory. We're going to have to add something to it. So this is where we had this add 0 operation. So that's kind of an identity function. We do the Y register, and then we want to do an increment. So there isn't an increment instruction, so we're going to basically just load a 1. We have to go through the ALU to get to the accumulator, so we're going to add 0 to it. And now we can actually do our increments. So now the accumulator is going to take its input from the data memory using that XY index. It's going to add the accumulator, which is 1. Then it's going to write that back, because it's got to remember the result. And then finally, we can update our X register. And that's basically going to have to be loading a 0 from the program memory, and then adding the accumulator, which has our result in it. And then we've updated our X register. And now we can do what we want to do with our X register. And then we've got to go through this whole process again to increment it to the next instruction. It can be improved. So you can use a 0 page. And in the Novasaur, the 0 page isn't so Y equals 0, which is normally what it would be. It's actually X equals FF. So instead of being the first page of this kind of bank 1 of the memory, it actually uses the very last column. We still have to specify where we're storing this, this X register value. So we have to still load Y. We still actually have to do this thing with the increments, where we have to load the accumulator with a function to increment. And then because we're not actually using the X register, we can update it now. So this last operation is essentially going to take the memory, add the 1, and then write it back to the memory and update the X register all in one go. So those 3 steps are combined. And that still looks pretty ugly, but that's actually basically exactly what it's doing. And I've got code which I actually pulled from the machine, which is doing this and with these 3 steps. And we'll take a look at that in a bit. But can it get even smaller? So this is another thing back in the 80s I was really interested in was actually taking the ALU and then putting it in that program memory. So not having a separate chip, but a single chip. So one bank would be your program, and another bank would have a lookup table to perform the ALU operations. So we had a very, very simple machine which had to have an ALU. And now it's even simpler, but in order to make this work, you actually now have to start adding some complexity back. There's a bit more state you have to deal with. So there's basically some different options for doing a lookup table. So the simplest one is like an 8 by 8 address space, so 64K of memory. So you put one 8-bit value on, say, the lower 8 bits, one 8-bit value on the upper 8 bits, and then you get a result of 8 bits coming out of this thing. But that's 64K per operation, which is kind of expensive. Especially back in the 80s, that was a 64K ROM just to do one operation wasn't really feasible. So you can kind of halve this. This is actually what I think what the Z80 does, where you have a 4x4, well, that's basically a 4-bit ALU. And so this is much, much smaller. This is only 256 bytes per operation. But it's very complex because you do 2 cycles. You have to basically take a carry, and then there's an intermediate result register which has to shift things around. So it gets very complicated. But there is kind of a trade-off. And so you can actually just treat one of the bytes directly. So the accumulator goes in as an 8-bit value, and then the other input is split into 2. And so what I do is add the first half using a 4K table. The result goes back to the accumulator, and then you recycle it to do the second half. You actually have to have a different table to do that, because you have to take into consideration you're shifting up by 4. This is like a quick example. So you have, the accumulator has, say, 29 hex. And then I have an HL register. So the other half of this is in a register which you can switch the nibbles. So you can either take the L or the H nibble, not bytes. So you're going to add the 8. So that 4K lookup table basically gives you that initial result. And then you just kind of recycle that and do another operation using a different table which treats the next nibble as if it was shifted up by 4. And then you get to this sort of 8-1 result. So that's actually not too complicated to do, so it's a good trade-off. So in that 64K of memory, of ROM, I can actually put 8 operations, but it still does that 2 cycle. So that's what the addressing looks like for the ALU. There's this B register, which is really just taking a copy of the ALU. We're going to update the accumulator. A copy of the accumulator. It's going to go into B, and then B is used as addressing when we go to update the accumulator. So you have to add this pipelining. The HL is 4 bits, and then that gets switched. And then your control word actually specifies one of 16 operations that can be performed. So that's kind of not too far removed, and it's not too much additional complexity. And that's where all that ALU kind of addressing lives. So there's an accumulator, that's the A register, the pipeline is a B. And then the HL register is basically an 8-bit register, but then there's this selector which selects one of the 2 nibbles. And then the ALU function comes through half of this chip. Those are the 4 bits. So this is the ALU functions that you get. So I have a move operation, which doesn't really do anything. So remember, everything has to go through the ALU. So this is basically just taking the H and the L and then moving them to whatever the destination is going to be. There's an add. So there's a problem with this. Because we're using this memory with an 8-bit, basically, output, if you add two 8-bit values together, you get a 9-bit one because there's a carry. So we only have 8 bits. So instead of having a subtract next, which have this, so you can do a 2's complement addition. You don't have to waste the whole table to do subtract. So this next one is actually, I call it arithmetic flags, and it gives you another 8 bits. So what you can do is you can do your add, and then you follow that add by this AF function. And that gives you another 8 bits of flags. So you get a carry, overflow, sign, 0 flag. And it also gives you the borrow flags if you're doing a 2 complement addition. 3 more classics. And then another thing about doing this kind of ALU in the ROM is you can pre-calculate all sorts of kind of crazy functions. So I have a wave table in here, which is used for the kind of audio system. And then this thing is used, there's sort of like a virtual machine we're going to get into, but this is how it determines which page it's going to jump to next, based on its current state. There's a multiply and divide, but it's really just nibble wide. So the multiply is really like multiplying 2 nibbles together and giving an 8-bit result. The divide is taking an 8-bit value and then dividing it by a nibble to give you a nibble. And so that fits very neatly in that 8x4 structure. A couple more specialized ones. There's a state machine used to sample the actual serial state. That's another sort of specialized table. And then the video timing tables live here. And then you're into the unary functions. I can never say that. So a unary function is like increment or decrement. So these others are binary in the sense that you have A plus B. This is just do something to A. So each one of these is 16 unary functions. And then there's actually 64 of these. So a lot of specialized ones. This last one is like the default set. And that's got sort of all the classics like increment, decrement. So there's actually 64 there plus these 12. The very last one is a kind of specialized hardware one. So I say altogether there's 75 operations supported by the ALU. And these are the default ones. So this default unary functions, the first one's the identity function. Increment 2, so adds 2. So this is basically add 0, 1 on 2. Decrement, 1's complement, so it inverts the bits. 2's complement inverts plus 1, so that gives you the negation. Logical shift right, logical shift left. And then there's a few specialized ones which are very commonly used. This one's quite handy though. So this operation takes the accumulator and it returns a 0 if it's 0 or it's -1. And I can do conditional jumping based on the sign of the accumulator. So if I want to figure out if the accumulator is 0, I can do this and then jump on the sign. So it's basically, if the sign is, if it's a positive result, it's 0. If it's negative, then it's not 0. And then these are some other things, swap nibbles, stuff like that. So yeah, there's, so the actual kind of control unit, I call it the execution state machine. So this is deciding what's happening on the various cycles. And so this is actually in a generic array logic. So it's configured as a 16R4, which is about circa 1978. So that is kind of error appropriate. So it just soaks up a little bit of the logic. It's got 4 bits of state in it, and it tracks the boot, whether it's booting up or not, and it's got 2 bits for the execution. And the execution sequence is as follows. So as we kind of went through with that kind of toy example, we do a fetch. So we're fetching the control word. That's that first cycle. We do have to do some kind of decoding. So we need a bit of time to do that decode. But during that time, we're going to also, if we're going to use the memory, we're reading the memory. We don't know whether we're going to use that yet, but we need time to actually access the memory. And so together, that sort of fetch read is a sort of one process cycle. And then the ALU is another process cycle. And that's the execute. So we're reading the ALU or the immediate value from the program memory if we're kind of loading a constant from the program. And then we're going to write the result back. So if we're going to update the memory, we need time to do that. And if we're doing this sort of 2-cycle ALU operation, we have to kind of do that twice. So that's 2 of these CPU cycles. But you might notice that we're doing program, data. And so because we have the Harvard architecture, when we're using the RAM is kind of idle, and vice versa. So basically, all of this is kind of up for grabs. So whilst we're fetching something from the ROM, like doing our program fetch, something else could read the memory. We could look up something in the ROM when the CPU is using the memory, go back and read, and then maybe we don't want to do anything. So there's like another set of cycles available. So we can add a second processor. We could actually add a second CPU to this and have it run concurrently. I call this a GPU, but it really isn't a GPU in a kind of modern sense. It's a transparent DMA controller. So it's transparent because it doesn't stop the CPU to access a memory. It's just running concurrently on these off cycles. And it can read the RAM whilst the CPU is reading the ROM. So this allows us to have a video memory that we can now scan without interrupting the CPU at all. And the CPU can update that memory. So you get these sort of very simple computers that have dual port RAMs, but this is kind of another way of doing it. So in order to use a video memory, we have to add another index. We have the XY RAM index. And now we're going to add a horizontal and vertical index register. The horizontal is actually a counter, a free-running counter, kind of like the program counter, but it's not. It's just running continuously. And then we can support a graphics mode where we're going to read 1 byte from the memory and output as a pixel. And we just put the output through some resistors to generate 256 colors. But another thing about this, and this is really the important reason for doing this, is we can build a native text mode because we have that ROM available. So we can read a code point, so that's like an ASCII value from the RAM. We can then look up glyph data in the ROM and then load a shift register, and then that can get clocked very, very, like 8 times the speed. And that generates like a native text mode. And then we load a color value as well, and then that can provide a foreground, background, which it's going to switch between. So what that GPU is doing is basically loading that ASCII, looking up what it would look like, and then using those bits to switch the colors to render that actual text. So that's what the GPU addressing looks like. There's actually 32K that's used. So there's a thing I call the scan register. So this is, it's updated by the CPU, but it's reading the fonts, glyph lines. So you can have 8 by 8-bit font, and there's also 8 by 16. So you need 4 bits for that, 3 bits for the other one, but I have another bit to select between the two. So I need 5 bits there, 8 bits for that B register. So that pipeline is used by both. And then the output goes to this glyph register, and we can select the font using this, the F register. So that loads the colors, but there's also a couple of bits available in there, so that can select between these 4 different fonts. So it's not too, don't worry too much about that. It's basically just almost like a simplified CPU. There's no program running on it, so it's basically just that H counter runs continuously, and then the CPU has to update that V register. And then the SF registers live there, and then this G register. So we covered quickly the memory. This is what the actual ROM looks like. So this is all the stuff we have in the ROM. Bank 0 contains the actual program that's being run. Bank 1 is used to actually just store 8080 machine code. That could be read sort of like the ALU. It's like another ALU. Then the ALU actually lives down here. So we have our 16 operations, of which 8 of them are these kind of extended 2-cycle versions, and then the font lives there. we haven't talked about the input-output. So we have to bit bang everything. So there's a couple of registers. One's used to read, and the other one's used to write. So there's bits that are coming in, bits that are going out. We have a line driver and analog switch to select between the two video modes. And there's a couple of transistors for controlling the keyboard. And that's where those live. This is what the EI and EO register looks like. So there's 2 bits for the keyboard, 2 bits for it does RTS, CTS flow control. So it only needs 4 bits on input. On the output, there's 3 bits that are used for the actual select between 8 banks of RAM. There's 2 bits needed for the video because we have to select which video mode we're in, whether we're doing text, and then which sort of video DAC we're selecting. We also have a bit where we can basically inhibit the keyboard to stop the keyboard scanning. So the keyboard's scanned every 15 times a second, so it's not continuously scanned. And so this is what the actual RAM looks like. Bank 0 has the video in it, and then we have 7 banks of 64K available. And there's an area needed for some system stuff at the top of that bank 0. This is where the control word lives. There's actually 2 registers, so it's not 8 bits, it's actually 16. But there's a set of instructions that can just use one of those bytes. So when the machine fetches instructions, typically there's 2 bytes needed, but if that very most significant bit is a 1, then what it will do is basically not load the second value. The way it does that is it just skips that cycle and it tri-states the control word, the second byte, so it all gets pulled high. So everything on that bottom row gets up this row. That all gets set to FF. So it's selecting the default ALU operations, and then you only get 4 possible destinations, 2 possible sources. And so that block there, there's 4 bits. There's 16 possible destinations. There's like basically 8 registers on board, and then there's an option to add another 8 possible registers on an expansion. 0 page, this is that WR bit sets whether it's going to write the result to the memory or not. And ZB is the 0 bank. So you can only use bank 0 with this like half instruction. Just quick rundown of these execution modes. So the first 3 bits in that control word specifies what it's going to be doing in terms of cycles. So the full 4 cycles, loading 2, fetch, 2, execute, that's 0. There's a couple 3-cycle ones where it just does single execution of the LU. And then there's these last 2, these are your shorter instructions. So there's 1 or 2 cycles to do this immediate load. So you can do a conditional jump in mode 5, looks at the sign. What it does, it actually skips the execute, it just jumps over the next cycle. And then these are the defaults. The last one is the default ALU operations. So I'll just sort of show a quick example of what that looks like. This is incrementing the X register again. So this is actually what the code looks like. So there's 6 bytes in order to do this example. So we're doing our immediate load, doing our immediate HL. So we're actually loading 1 into H, and then we're doing this FNH operation. So 1 in that default set of instructions is an increment. And then this is how we do that. There's actually, I think it's about 17,000 possible instructions or combinations of things you can do. There's 65K, but of which about 17,000 are kind of valid. So how does it actually work? So yeah, that's the CPU. It's super basic. There's no, we've got the keyboard interface, serial interface. There's no UART. There's no like video chip, no VIC or SID chips or anything like this. So all of this has to be bit banged. So the software requirements come like this. So We have a lot of concurrent protocols, so there's a lot of state. There's a lot of critical timing, so there's a lot of control needed. We can't really interrupt it, so we can't like let load a user's program, start executing, and then interrupt it like 30,000 times a second to do video timing. That's just not practical. So we can't yield to a user program, so we cannot run a user program actually on the hardware. We also want a stored program, so we want to be able to load a program at runtime, so it has to live in the data memory. So that means we need to have basically a bytecode interpreter and a virtual machine or virtual CPU, and preferably using an existing instruction set architecture. So this is the actual software stack. So you have the hardware, these are the interfaces, and then what we're going to do is put this hardware abstraction layer on top of that. So this is kind of like a virtual machine, and it has a bytecode interpreter that's going to interpret the memory as 8080 machine code. Originally, I was looking at doing Cosmac, because it's really simple, but I decided there's a lot more for 8080. I also thought about 6809, but this is where I ended up going. And then just to make life even more convoluted, there's a microkernel, we'll get into this. This is basically to allow you to do memory management. And there's a disk. It provides timers, and it controls TTL, the serial and console. And then we have CPM on this. So the BIOS actually talks to this microkernel, that talks to the hardware abstraction layer, and then it's talking to the hardware. And then finally, you actually have your application layer, and so your user program can run there. Whoops. So this is the most kind of overhead is really doing the video timing, and this is kind of what's going on in typical VGA-style video timing. You have to fly back at the end of the line. This is the old sort of CRT way of doing things, and then fly back at the end of the page. I show them at the beginning. So there's a vertical sync pulse and a horizontal sync pulse generated by the machine, and that tells a monitor all the information it gets about what's happening in terms of timing. So whether it's when to start the line, when to start the next frame. And there's some blanking. I don't really do the blanking. The blanking's done just by writing a bunch of like zeros to the memory, so it doesn't output anything. There isn't a lot of logic to do that. It actually supports quite a few different video modes. So VGA, 640 by 480. There's a 75 Hz version, SVGA, and also XGA. Now I have a fixed dot clock, and that's closest to this VGA at 75 Hz. So if you do it at 60 Hz, you actually get 104 columns of text. And the Super VGA, which technically would be 100 columns of 8 by 8 glyph text, that actually you actually only get 80 columns. And then this XGA mode, you've got a lot more rows, and actually you're down to 64 columns. But you can actually run CPM on 64. And these are the lines, the actual total lines for the video frame. So video control, we have to update those indexes. So that's scan index, which is indexing the glyph data. The vertical register, which indexes which kind of row in the memory which the video is going to output from. When you update the V register, it resets the H counter. So you have to do that. To get the timing right, you've got to do that precisely at exactly the same time every time. So we have to count the lines to figure out like when we're actually going to reset the vertical. But the trouble with that line count is it's greater than 9 bits, which means you can't do it with a single byte. So you have to use an ALU lookup. So we can take advantage of our ALU using our 8 and 4 bits. So we have a block count, and that will be 8 bits and a line count. So instead of counting all of the lines, we're going to break up the lines into blocks. And those blocks will be, typically it's going to be 2 bits, like 3 or 4 lines, but I'll show you what that looks like. And this is where our vid function comes in. So we break it up into these blocks of lines. So we're counting blocks. Each block has several lines in it. So this is one of the most common modes where you have 4 lines per block. At the beginning of each line, you have to generate that sort of we'll use that vid function to generate the sync pulse and update the vertical counters, scan counter. We also sample the communication interfaces on that using the com function. And then we're going to reset the count at the beginning of the frame, and then count the blocks. So we have to have a little bit of code. Now, all of this space is available to actually run the user's program. So we can run our interpreter in this. And there's a little bit more to this. So we're going to have this virtual machine cycle. So we have these lines, but we can also use columns as well. So we break up the lines by tweaking the actual video modes. So VGA, which is about 31.5, we can push that up to 32, which is 192K divided by 6, divided by 5, divided by 4 for these three. There's a speed limit on the machine, which would be the speed limit of the memory. The way it's working is actually, things are kind of pipelined, so you can push it very close to the actual speed of the memory, which would be about 18 megahertz. You don't want to go that fast, but I'm able to get it to go at, well, I can get up to 17.5 megahertz, but it's not too super stable. Originally, I was thinking 16, but I'm doing 16.5. So I start with a 33 megahertz crystal. That gets divided down. So the processor is running at 8.25 megahertz, and then the magic number is 43, not 42. So 43 cycles per virtual machine. So the virtual machine cycle has 43 cycles of the native machine code. And that results in 191.86 kilohertz. That's effectively the clock speed of this virtual machine. But each one of those cycles, you have 43 cycles worth of native code that you can run. So the native CPU is about 3.5 MIPS, whereas this is 192 cycles. And this is what the actual video modes look like. So this is the VGA, so it's 3 by 6. I actually add a little bit of time at the beginning, so I jumped through an intermediate page just to delay it a little bit and actually bring it perfectly in line with VGA timing, because some monitors are a bit finicky. So this is like the default. This has a block rate of 10,659 blocks per second, which isn't very useful. The SVGA looks like this. This is 4 by 5. So that's 20 virtual machine cycles per block. And that's pretty close to 9600 baud. So the block rate is used to actually do the serial communications at 9600. So there's 160 blocks per frame, 161 blocks per frame. So in order to keep track of where we are in the cycle, we need to count the lines and also the cycle within the line. And so there's this byte stored in the 0 page called the virtual machine state. And those 4 bits, I call it the mode line, because that tells you what line you're on, but also which video mode. There's different kind of counts it can do. So in the VGA, the mode lines count 012, 012, and then it will count the cycles 0 through 5. There's 2 available for the next mode. So it counts 3, 4, 5, 6, and then it's doing 4, and then that cycle. And then for the XGA mode, it's doing this count. And that's essentially what goes on. There's an extended bit, so I actually have an extended set of instructions. And that bit there will tell the machine which one to use. And then this is basically how the virtual machine works. It might be a bit hard to understand what's going on here. These represent sort of sections of code. So each page is made up sort of like this. So you'll have a page which will have maybe only 18 bytes of code in it. The first few bytes are going to increment that virtual machine state. You've then got about 30 cycles of actual code you can run. And then at the end, you dispatch. And that then figures out where you're going to go next. You're going to load the next instruction. You're going to do the video timing. There's a sort of a double wide one, so you increment 2 cycles, and then you have about 72 cycles of code. There's also a 3, so you've got over 100 cycles of code that you can pack in there. So each page in the ROM is essentially a virtual machine operation. There's about 84 pages, and each one is basically interpreting 8080 machine code instructions. And then, So I think there's probably about 80 actual instructions. I mean, there's 256 bytes, but there's a lot of move operations. So you only need about 84 pages of code to implement the whole 8080 instruction set. And there's a few extra ones in there because some things get broken up into two. And so that dispatch function, that's in the ALU, sorry. Yeah. So the page, it calls this dispatch and it returns the page number to jump to. And the input to that function is this virtual machine state and the instruction. So it takes the 8080 machine code instruction, the state, and then it says, does it have any cycles available to execute that code? Or you might have come to the end of the line and it has to do a horizontal sync. And so that's all pre-calculated and loaded into the ALU, and it uses that to basically drive that virtual machine. And so this is actually what that execution sequence looks like. So in this video mode, we have these 4 sync pulses. We have to use that first available cycle just to update the block count. And then all the rest are available. So what I've shown here is that you're going to fetch an instruction. So the fetch is a separate cycle. So you do a fetch, that's 43 cycles. And then you can do an execute, which is, say, another 43. But the next instruction I fetch is a double cycle one, so that takes 2. Then I fetch, and I get maybe another 2 cycle one. So that has to skip to the next line. So it inserts an idle cycle. So it can't execute 2, it'll miss the sync pulse. So it has to just kind of burn that. But there might be a little bit of room, because what you'd have to do is you have to pack the code to fit in these kind of blocks. But sometimes you have some space at the end, and you can prefetch the next instruction. So some of these, they'll do the execute, and then they'll prefetch. So you go straight back to the execute. So there's quite a few that are like that. So there's some where it does fit into that 43. Some it's a little bit too big, but not huge, so you can then prefetch. Some need 2, and there's a couple that actually use 3, which is very inefficient, because if you do that halfway through the line, sometimes you have to skip 2 idles. The XGA, which has those very short lines, there's about 20% of the cycles are burnt this way. So it's not a very efficient mode. So the threads. So, I've been showing these diagrams with these 4 sync pulses, but each one has a special kind of set of features. So it does its sync, and then there's a byte available. There's a mode byte which it checks, so you can turn things on and off. So that first line is reserved for managing the block and also the virtual machine. So it'll update the block count every cycle. If it gets to the end of the frame, it will then add another cycle to update the frame. 15 times a second, it actually adds another cycle to start the keyboard scan. And there's also a real-time clock. So this can go up and consume all of those cycles every 6 seconds, and it updates these counts to keep track of time. There's basically 3 timers. The audio is very labor-intensive because it's all doing math to calculate the waveform. So if you turn on the audio, it uses up 2 cycles immediately, and you can add up to basically three voices of audio. So with all 3 turned on, it takes all 4 of those cycles. And then when you turn on the actual serial communication, it does sample the serial, but it doesn't do anything with it. So you have to consume a cycle in order to handle the actual serial. And so that's what's happening there. So not all of this will get turned on at the same time, but if you do, you only end up with 6 available to run your CPU. So the more features you turn on, the more you kind of take away from the resources to run the actual code. I haven't really mentioned the audio, but the glyph register during the blanking period is used to basically read a sample value, and there's a little filter and amplifier. So it's actual real pulse code modulation, so you get like a microsecond pulse at various values using this little R2R DAC. And then that has to amplify it and filter it out. There's also an expansion port. So there's basically another 8 possible registers you can use. And they're actually mapped to the 8080 as ports 1 through 7. So port 0 is kind of reserved. And this is how the hardware abstraction happens. So basically, the 8080 has this, essentially a separate address space. There's 256 ports. So those first 8 are reserved for this expansion board. So port 8 is the serial receive and transmit. So what you can do is you can say to the 8080, like, give me the next byte of serial data, or write this byte. And then that abstraction layer takes care of managing the buffers and sampling and all that. There's a console as well, so it keeps track of a cursor position, so you can like send stuff to a console, and it'll update the console, the actual screen. It updates the memory. That's all taken care of. And then there's a couple, 10 and 11 you use for controlling resources, turning on how many audio cycles are happening, or enabling, disabling the actual serial. And then you can actually access the 0 page this way, so there's a whole bunch of bytes available on the 0 page, and that's things like controlling the audio, so setting up the channels. You're just writing through this like I/O mechanism. And then there's some additional things which only read only, like the real-time clock and the position of the line counts. And so with CPM, you need a disk drive. I didn't want to add an SD card, so this is a modern memory, so it only uses 4 microamps in standby mode. So when you push the power button and you click it off, it puts this into standby, and there's a CR2032. And that could potentially back up that RAM for about 5 years, maybe, but at least a couple of years. So that's a pretty persistent thing. However, if your program crashes and scribbles all over the memory, it's kind of wrecked. So you have to have some kind of memory management system. But remember, we're in software. This is like a virtual machine, like a Java JVM kind of thing. So we can pretty much do what we like to segment that. We're not running on the hardware. So we can add all sorts of different features for doing that. And the way I've actually decided to do it, actually I'll get into that next. Yeah, this is what the actual RAM disk looks like. I take 4 banks of memory. Each page is like 2 records in CPM. They're 128 bytes each. And I stitched the 4 pages together to create 8 sectors of 8 sectors per track, 254 tracks. So there's 2,032 records on that disk, about 254K, which is about right for a 1970s. But the memory management, the way I've actually done it is actually, I can do preemptive multitasking on this thing, because again, it's all in software. So I assign each one of those 64 banks of memory to a separate CPU, which sounds kind of absurd, but it's actually not too difficult. There's a very quick way with the instruction set to switch. If you keep that Y register the same, you can actually read and write from 2 bytes adjacent to each other, so I can swap the state very quickly. So what it's doing is it counts 100 blocks. When it gets to the end of that 100, it context switches to another CPU, and you can specify that in another table. So the RAM disk is 4 separate CPUs, each managing 254K of RAM. And we actually have 2 instances of CPM. So if you go through the serial terminal, you'll get a CPM prompt, and that's separate from the one you'll see on the actual CRT. And then CPU1 is used for that microkernel. So the microkernel does all of the CPM is talking to that microkernel to get to the other CPUs. So that's actually what that system memory looks like. So it's a pretty big slide. But basically, there's 16 kind of columns. Column 0 isn't really used, but there's basically, you have a CPU and there's a little bit of shared memory. So each CPU can write to its own shared memory. The kernel can actually transfer stuff between them. The serial keyboard buffers are in there, this context switch sequence. So the actual virtual CPU that's running is in this 0 page. So what it's doing is it's just context switching by copying from the current state into one of these, and then copying the other one back in. And that can be done in under 1 block. So you can context switch once per block. So that would be potentially 9,600 times a second. So you can yield and then context switch right away, and that's how a lot of it works, where it goes to see whether it's got anything to do, and it just yields back, and it just uses up one of those blocks. So it's a quick example of a read and write. So this is the A drive. That's the A drive is the RAM disk. And so what the CPM will do is it'll talk to the kernel and say, I'm going to get this record. It doesn't know where it is. The kernel's going to figure out that's on disk segment 5. So it forwards that on. So the disk CPU 5 will then copy that into its shared memory. The kernel, and then it will return. The kernel will be like, okay, I'm going to copy 5 to 2, and then it sends a return back to the CPM and says, okay, the record's in your memory. And then the CPM will copy it into its kind of file system. The write's a bit easier, where CPM's going to write it to its shared memory. You're then going to say, put that on the disk drive. Kernel figures out where, copies it across, and then that CPU will copy it down into its file system. There's a few steps here, and this is the issue with the microkernels, where they tend to do a lot of, it's not like the monolithic one where it's the actual kernel's accessing the disk drive. The kernel here is a traffic cop. But this can run at about 6 kilobytes per second, which is not too bad. It's about, it takes 10 seconds to load or save 64K, which isn't outrageous for the 70s. And then finally, there's a B drive. So that storage area in the ROM contains the kind of classic CPM utilities. I wanted to ship this with BASIC on it, so I've only got 8K. I tried to get the Microsoft one, the original kind of like Albuquerque sort of thing, but it didn't really work. But I got the IMSI, which is from 77, and that's actually working. So CPM 22. It's about 7K DDT dump. So all of the CPM stuff. This is like the very final piece, like 4 years later. This is the last piece. So there's a utility function. So typically we'll have a format command that you can format the A drive, and also to do serial transfer of files in binary mode. That's like the last piece. That B drive also contains a page for the boot code, the actual disk client code for managing the file system. There's the kernel, it has 2K available. That kernel's actually 600 bytes, and it's doing all sorts of magic. So it's like really, really simple and stripped down. It could get up to 2K, which is pretty outrageous. There's also a 8080 machine code monitor, which is actually what I demoed 18 months ago here. That's like as far as I got, but that's been very useful. So that's all on that 64K chunk of memory, but the CPM sees a 60K B drive. And then there's going to be a kit. Well, essentially there are kits, but the software's not quite done. It's maybe a few weeks away. And that's what it looks like. And I think 3 minutes. Yeah, this thing switched off. I've been like trying to, I might have powered off, I don't know. But so yeah, that's the project. I had to kind of still fairly high level, and I'm sure it's kind of might have gone over the heads a bit. But I'll be here all weekend, and if you want to go into any more details, what I skimmed over is there's like a lot of depth to all of these things, like the actual implementation. There's all sorts of extra things, like the video table. It has like two things inside it. It uses basically one table to index it to another. So it has an indirect indexing system, and it can do 96 different kind of timings and video combinations. It's all a bit ridiculous. So yeah, this is the sort of the business of solid-state machines. I've been documenting this on Hackaday since day one. So if it's very early on, it's sort of a stream of consciousness. So there's like some early ideas which disappeared. But generally, each log has, I would say, a complete idea, although the final implementation might have drifted a little bit. And then all the code is in, if you actually want to see what it looks like. So it's about the actual virtual machine. So that virtual machine, it is pretty much the only program that ever gets written to run on the hardware, and then people would use the 8080 machine code. I don't think normal people would actually want to get into the weeds. It's really obnoxious to break everything up into these 43 cycle blocks. But that code is about 5,000 lines technically, and it took, I don't know, a couple of years to write. A debug, actually, it took 6 months to write and 18 months to debug it, I think, something like that. Yeah, so this is a very big software project. But now it's actually done, it's really cool. So I'm thinking about, I wanted to do a sort of surface mount version. So this is the machine. So I got this is a standard case you can get. So I'm not printing anything. I have a CNC machine I can engrave. That's what it looks like. I'm thinking about doing a surface mount version, but I want to take it to another level where I can actually break all this down into single discrete gates, and you can get these little SOT23 packages. It would have about 350 of those, and it could theoretically work. So that maybe end of the year I'll start looking at that. But I think that's it.
That was a very, very lovely presentation. Thank you very much, Alastair.
Okay.